Welcome to the ninth tutorial session of the SWAYAM course, Problem Solving through Programming in C. This is a SWAYAM course. I have already said that it's a SWAYAM course floated by Professor Anupam Basu from Department of CIC IIT Kharagpur, and I'm Siddhant. I'm the TA who is in charge of taking these tutorial sessions, where we'll be discussing some questions and concepts related to that particular week's lectures, and we'll solve a few questions which might help you with the assignment as well as with the final exam. So this week we looked at week 9 we looked at binary search and the different sorting algorithms such as insertion sort and selection sort. Uh, we also looked at macros. So let's solve a few questions based on that. So we'll be discussing uh, selection sort and insertion sort in detail, and we'll be looking at their time complexities, the best time complexity, the worst time complexity, and so on. Alright, so let's get started. So the first question is that of a macro. So basically what we are doing, what the question asks from us is, what is the error in the following program? So here we have defined this macro. So the macro here is this SI. It's a inline function. It's a macro inline function. So it takes three parameters, and then we are inside SI. What we are doing is we are declaring float SI, and we are setting float SI to P into N into R divided by 100. Now in the main function we have three different floating point variables, which is P set to 2500, R set to 3.5, and N is set to 3. It is an integer variable. So we call now A equals SI, which is the macro, with this values of P, R, and N. We call the macro, and then we again call this with 1500, 2, and 2.5. Alright, so what will be printed when we print A? What will be printed? Or what will be the error? Option C. Why do you think so? Okay, okay. So basically, it's if you give the curly braces, then it won't be an error anymore. Right. Right now, if I write this as this float Si equals P into N into R by 100. So instead of this two statements, if I write it directly like this, float Si equals P into N into R by 100. So should it be okay? You can try running this and see what it gives you as the answer, or like what it exactly gives you as a result. You can try running this. So any of you can try running this on a compiler and see what the error is. So there are a few things to see from this question itself, like how we can use macros and so on. So yeah, just try this out. Does it give an error? So what happens if I write only this? Okay, this also throws an error, right? This is also error. So here also it will give an error. Now what if I write simply this, define Si P comma N comma R P into N into R by 100. What if I write this? Just this much. Can you try this out? So this will be a legal expression. This is no error. So basically we just wrote the return value instead of writing the float. So basically what I am trying to say here through this is that we don't really need to define a variable and then like this si is supposed to be returned from here, but we don't really need to define a variable inside a macro. So how we can use, if it is an inline function like this, so here we are kind of calculating the simple interest, right? So we just write define the function name with the input parameters. The input can be anything, p and r. As you can see, I have not specified any kind of the data type here, and simply I just write what I want to return just after that, p into n into r by 100. So then it works fine. So if we write float si and we define si at all, so basically this declaration of si is the error here. Okay, so the answer was correct, but yeah, so it's more or less you have said the correct answer. But this part also that you said would be the curly brackets is, it's not the problem with the curly braces, but the problem is with the declaration of the si, which is this small si. Okay, so if you want to simply write an inline function here using a macro, you can just write define si in braces in parenthesis p and r, and then just write the return value p into n into r by 100. That's all, and the code will run just fine. So here the error is the declaration, or I would say the multiple declaration of the variable si. Is that clear? Okay. Now let us move on to the next question. So the question asks, which of the following is a disadvantage of linear search? So if you remember linear search, basically we had say we have some array 10, 15, 3, -5, 19, 21, something like this, and we have a key which is say -5. And linear search, what it basically does is it goes, checks the key with the first value, then with the second value, then with the third value, then with the fourth value, and so on. So it traverses the array in the same in a order, either in the ascending order or in the descending order. So and it checks every value along against the key, and wherever it finds the match, it will just inform you that yes, now I have found this particular key in the array. So that is the linear search. So what is the disadvantage of the linear search? Right. So so can you tell me what is the time complexity of linear search, like the O of n? Yeah, that is the average time complexity, right? Right. So the correct answer here is greater time complexity. So linear search, because it checks one by one with each of the elements. So consider this is a small array which is like 6 elements only, right? It's a very small array. If I say I have an array with a million elements, right, and I want to do a linear search, so it will go and it will have to check against the key against each of the values there. So if say the last element is my key, actually if the key is present in the last element, the conditional checking has to be done 1 million times. Only then it will find the key and it will say that the search is complete, and we have found like one occurrence of this key, right? So it has to do that 1 million times. So the larger the array, the more the time complexity, that is the time taken by the code to run to find out the key or to say that the key is not present, will be higher by order of n. That means uh, when I say order of n, that means n is the number of elements in the array. So it has to go through each of the elements. So it has to do n number of conditional checks. So because it has to do n number of conditional checks, that is the time complexity of the linear search. So that is the disadvantage of linear search. So there are better techniques than linear search, such as binary search, right? Binary search we have studied in this lectures. which basically works on sorted arrays. So in a sorted array, we can binary search is much faster than the linear search because it just keeps on dividing and checking. Okay, so we'll look at binary search questions as well later on. So current for now, is this clear that why the time complexity is a problematic part of the linear search algorithm? Yeah. Okay. So yeah, now we have the next question asking the exact same thing. What is the best case and the worst case time complexity? So whenever we are asking complexity, it's basically time complexity. We are talking about time complexity of ordered linear search. So what do you think? The best case and the worst case. Right. So O of 1 and O of n, that is the correct answer. So what is the best case? So we have say the same matrix, say something, and say the key is 20. Okay. So if the key is 20, then this is the best case because uh, like we checked with the first conditional and we got it. That is the best case. So it is O of 1. We only needed to do one operation in order to get our key. So we are happy. It's O of 1. One computation, we are done. And the worst case is if the key was say 21. If the key was 21, then we would have to go through all the elements. So there are 5 elements here, so we would have to do 5 conditional checks and then we would have got our key. Okay, or if the key is not at all present, say the key is 45, which is not here, so we would still have to do all the conditional checks of all the values. We have to check the key against all the values and then we say that okay, it's not present in the array. The linear search did not return uh, any indices. That means it's not present, the key is not present. So that is O of n, because we have to do n conditional checks, that is 5 here, 5 conditional checks in order to comment that either we got the key or we did not get it, it is not present. So that is the best case and the worst case time complexity of ordered linear search, that is O of 1 and O of n respectively. Is this clear? Yeah. All right, now uh, back to more familiar topics. So here we are again looking at pre-increment and post-increment operators. Uh, I'm sure you have solved a lot of questions of this kind by now, so this should be quite easy for you. So we have an array of size 5. It is an integer array, and you have the 5 elements 1, 2, 3, 4, 5. So indices, as I can say, is something like this, right? And we have an integer variable a. Now the first statement it says is a of 1 equals plus plus a, sorry, arr of 1 equals plus plus of plus plus arr of 1, right? So this is the first statement. So what will happen here? So meanwhile you can solve the entire thing and answer. I'll be solving it step by step here. So arr of plus plus is there's a pre-increment operation. So pre-increment operation, if you write it like this, it's fine. So it will increment the value of arr of 1 by 1 unit, that is arr of 1. So arr of 1 is 2. So now the array becomes 1, 3, 3, 4, 5, right? So this statement, it becomes 1, 3, 3, 4, 5. This is your array. In the next statement, what does it do? It says a equals arr of 1 plus plus. So it's a post increment operation. So what happens here is a will get the value of arr of 1 and then arr of 1 will increment by 1. So arr of 1 is currently 3. So a will get the value of 3 and then arr of 1 will become 4. So basically your array now is 1, 4, 3, 4, 5. Alright. Now what happens next? So this is pertaining to this step is pertaining to this, and then what happened? The next step is arr of 1 equals arr of a plus plus. So a plus plus is a post increment operation again. So this will be treated as ARR of 1 equals ARR of a, and then a will be incremented by 1. So what does this mean? This means ARR of 1 equals ARR of a. A is 3. So basically, what is the a of 3? A of 3 is, the value is 4. Okay, it's 4 currently. So this is 0, 1, 2, 3. The index 3 has a value of 4. That will be copied to index of 1. So it still remains 4. 1, 4, 3, 4, 5. Still the same, because this value gets copied here. And as you can see, both are having the value of 4. So it doesn't matter. It gets copied however. So 1, 4, 3, 4, 5. And then the value of a becomes 3 plus 1, 4. Okay, because it's a post increment operation. Now when you print a and ARR of 1, what do you get? A is, the value of a is 4, ARR of 1 is also 4. So the answer here is 4 comma 4. Is this clear? Yeah. So this is how this would happen, and this also would happen like this. A equals ARR of 1 followed by ARR of 1 equals ARR of 1 plus 1. Okay, this is the order in which this would happen. All right. Uh, let's look at the next question. So we are finally coming to the insertion sorting and searching algorithms. So yeah, let's have a look at insertion sort. So this is our array, initial array, which is 8, 3, 5, 9, 4. Okay, 8, 3, 5, 9, 4. Now we want to sort this in ascending order using insertion sort. So which of the options gives the correct order of insertion sort that happens? So what happens in insertion sort? First of all, so we take the second element as the key, right? We compare it to the element before it. We see that, okay, so this is ascending order. So we need to see the minimum element should be at the top, right? And the maximum element should be at the bottom. So we take the second element as the key. We check with the previous element, that is 8, and we find that there is a need for swapping because 3 is less than 8. So we need to swap it. So this, we swap this to, okay, and that becomes 3, 8, 5, 9, 4. All right. Now next what we do? So what is our next key? Our next key is that is the third element. This is our key in the next step. Now we compare it to 8. We compare it to 8, that is the element before it, and we find that it is less than 8, so we need to swap it. So this will go here, this will come here. So that becomes 3, 5, 8, 9, 4. Okay. Now what is our next key? Our next key is the fourth element, that is this 9. 9 is our next key. So we compare it to the element before it. We see that there is no need for swapping because 9 is greater than 8 and we are sorting it in ascending order, so we don't need to change anything. So we'll just do nothing this step. We'll go to the next pass. So this is the first pass. Okay, yeah, this is the first pass, this is the second pass, this is the third pass, and then what we will do in the next one. So 8, 9, 4. So 4 is our key in the fourth pass. Okay, and in this pass we will have a few sub steps, but finally what the pass does, it will check with 9. Okay, it will find that 4 is less than 9, so it will swap this to. Then after it reaches here, it will check 4 against 8. So it will find that 4 is less than 8, so it will again swap. Then it will check with 5. It will find that it's smaller, so it will again swap with 5. So finally what happens is this goes over here, this all gets shifted down. Okay, this is what will happen. So we get 3, 4, 5, 8, 9. Okay, so what is the correct order? So in the correct order, the first is this. So after the first pass, so when the question asks correct order, right? So we start from here. The first pass is done on this. After the first pass, you get this, which is 3, 8, 5, 9, 4, which is here, here. Yeah, basically in three options. Then we have 3, 5, 8, 9, 4. 3, 5, 8, 9, 4. We have still two options here. Then we have 3, 5, 8. Okay, yeah, still 3, 5, 8, 9, 4 is the same. So doesn't matter. Okay, then we skip on to the next pass. That is 3. Okay, then we have 3, 4, 5, 8, 9, which is this. So this in the second, so the second could also be an answer, but you need to understand that the correct order, when we are asking for the correct order, we just mean the overall pass. So this entire swapping thing itself is one single pass. Okay, so here the answers, if you see, you can see the 4 is actually getting swapped with 9, then it is getting swapped with 8, then it is getting swapped with 5. So that happens internally, but this 3 together will be considered as one pass of the system. So after this particular pass, it will come out to be 3, 4, 5, 8, 9. So here the option A is the correct answer. Is it clear how insertion sort works? Why not B? Okay, so okay, so every sorting algorithm has, like, you we call them as pass. That means it goes through the matrix and goes through the array and does. So one time it goes through the array, it's called one pass. Second time it goes through the array, it will be called second pass. Third time it will go through the array, it will call third pass, and so on. So in the first pass here, and so here the pretty much up till pass 3 it is pretty clear, and here the options are not considering pass 3 because it's basically does nothing. So from third pass to fourth pass it's basically does nothing, so we don't have an option which has that one. Now in the fourth pass, what happens? So this fourth pass, basically here it has 3 steps. So the fourth pass itself has 3 steps. Okay, the fourth pass has 3 steps where you have so from this you go to first this happens, then you will go to 3, 5, 4, 8, 9. This will happen, then you go to 3, 4, 5, 8, 9. So this entire change, this all this swapping, okay, first it swapped here, then it swapped here, so it went here, it went here, then it went here. So all this swaps, all of this swaps, this constitutes one single pass because the algorithm goes through the array one time during this entire 3 steps of swapping. The algorithm goes through the array only a single time. So it is all these 3 steps of swapping will come under the fourth pass itself. It will not be a separate step on its own. So when we are writing the insertion sort, we are saying that this is the first pass, this is the second pass, third pass, fourth pass, and so on. So this is this all this swapping is constituting under the fourth pass itself. So the answer here, the that is why option B won't be the correct answer, because it again subdivides your fourth pass into 3 different steps. Okay, but it is considered as a single pass, so it will directly will write as 3, 4, 5, 8, 9. Is that clear why option B is not the answer and option A is the answer? Okay. All right. Now let's look at a question from binary search. So I was talking about binary search earlier, and I was talking how it works only on sorted arrays. Okay. So that is a limitation of binary search, that it will work only on sorted arrays. That is very important to remember. So here we have a sorted array. So we have 45, 77, 89, 91, 94, 98 and 100. Now this is our array and the key is 100. Okay, so this is the element that we are searching for, whether it's present there or not. So what do we do in binary search? We first divide the array into two parts. So here we have 7 elements. So we will go for the fourth element here. Okay, we'll first go to the middle element. First middle element is, so this is the, let's say, the first pass of the array. So in the first pass we will go to the middle element. The middle element is the fourth element here because there are 7 elements. So the middle one is the fourth one. So we'll go to the middle element. We'll check whether 100, whether this is 100. No, this is not 100. Is 100 greater than 91? If it is greater than 91, we just consider this part. If 100 is less than 91, we just consider this part. Or rather, I should not say it like this. I should say we'll check it with the key. So if the key is greater than 91, then we just consider the remaining part of the array. If key is less than 91, then we consider the upper part of the array. Okay, so basically this is why it is called binary search. It will divide the array into two different parts. That is why it works only on sorted arrays. So also here, as you can see, you need to know in which way it has been sorted. So is it a ascending, has it been sorted in an ascending way or in a descending way? Because that will matter. If it was sorted in a descending way, then the other thing we would have to see the other way. If key was greater than 91, we would have seen the upper part instead of the lower part. If it was a descending manner, it had been sorted. But here it has been sorted in an ascending manner. So if the key is greater than 91, that means it occurs in the part, if at all it occurs in the part after 91. So we just consider this part to be our array now. So now we have 94, 98 and 100. Okay. So again we go for the middle element. So the middle element is here is 98, right? So the second middle element is 98. So this is the second pass, and we check 98 against the key. So if key is greater than 98, then we'll go to the remaining part of the array after the 98 value, and if key is less than 98, then we would go for the part before 98. So now we find out that it is greater than 98. Now greater than 98, there is only one value, so we directly check in the third pass. We'll just directly check 100 against the key. So we'll check if this is equal, then we have found it. If it is not equal, then the key does not exist in the array. Okay, so this will be in the third pass. Alright, so the question asks what are the mid values in the first and second iterations of binary search. So basically in the first and the second pass, what are the mid values that we are getting? So the first mid value, as you can see, is 91 and the second mid value is 98. So answer is option A. Is that clear? Okay, so I will explain again. So this was our matrix: 45, 77, 89, 91, 94, 98 and 100. We have a key which is 100. Now what our objective is to use binary search to find out whether this key exists in the array, and if it exists, where does it exist. Okay. So what we do first in binary search, it works only on sorted arrays, and we know here that it is a sorted in ascending order. So what we will do, we will find the middle element of the array. Okay, so this is an array of 7 elements. So fourth element is the middle element. Okay, so we'll take the we'll go and check our key against the middle element. So the first middle element is 91. Okay, that is the, so basically if you have 7 elements, then fourth is the middle element. So we check the key against 91. So the key is not equal to 91, that is okay. Now if it is a sorted array in an ascending order, that means all values higher than 91 will occur after 91, right? And all values lower than 91 will occur before 91. So now we found out that our key is actually greater than 91. So it should occur, if at all it occurs in the array, it should occur after 91. So we only consider the array after 91, the array elements after 91. So those array elements are 94, 98 and 100. Okay. Now 94, 98 and 100, again we go to the middle element. So what is the middle element? So there are three elements. The second element is the middle one. So the middle element is 98. We check that is our key equal to 98. No, it is not equal. Now is it greater than 98? Yes, it is greater than 98. So if it is greater than 98, then it can occur only after 98, not before, because the array is sorted in an ascending order. So if the key is greater than 98, then it can occur only after 98. So we'll go to the part of the array after 98. So here we have only one element. Now we check the key against this element and we find that yes, it matches, the key matches. So we have found our answer. So basically you can see that how it is better than linear search, because how many checkings did we do here? We found out the middle element of the array, we checked against the middle element, and we found that it's greater than the middle element. So we just did one conditional checking. Then again we did a second conditional checking here with again the middle element, and then a third conditional checking, and we found our answer. So in for an array of 7 elements, we found only with 3 conditional checks we found our key. While for a case like this, in the linear search, it would have taken you 7 conditional checks. You would have started from the beginning, checked 45 against 100, 77 against 100, one by one you would have checked, and finally at the end you would have found that the key is equal to the last element. So we found it. So you would have to do 7 conditional checks there. But here with binary search, you only need to do 3 conditional checks. So you can see why binary search is better than linear search. Okay, so that is the concept of binary search clear? Okay. So here the question asked for the mid values only, not how many steps we took and whatever. So mid values in the first and second iteration. So first iteration our mid value was 91. In the second iteration our mid value was 98. So that is what our answer is. Okay. Okay. Now let's classify this linear search and binary search as the types of algorithm. So there can be different types of algorithm. Now, linear search, what kind of algorithm do you think it is? So, linear search is actually categorized as a brute force algorithm. Why? What does it mean by a brute force algorithm? A brute force algorithm basically means that it will try out all combinations, all possible combinations, and won't care about time complexity. So basically that is what linear search does, right? It will check with all the elements one by one and just all combinations it will try. So all steps it will do, it will check with one by one all the elements, and then it might find the key, might not find the key. So it is a brute force type of algorithm because it tries out all possible steps and it does not care about time complexity. That is why it's a problem with the linear search, that you have high time complexity compared to other searching algorithms. Now what about the binary search? So in binary search we divide the array into 2 parts. So we of course we need a sorted array. We divide the array into 2 parts, then we consider only one of the parts, and then we divide it again and again and again. We keep on dividing it until we have only one element left, and if that is our key, good. If it is not, then the key does not exist in the array. So it is a divide and conquer algorithm. Because why? Because we keep on dividing the array into smaller parts and solving the problem, right? So we'll keep on dividing until we have one element, and then we will check if that element is our key, then we are on the correct path. Alright, so that is a divide and conquer algorithm for the searching part. Now what about sorting? So there are also divide and conquer sorting algorithms. You can, it's not part of the course here, so I'll not cover them, but you can try to learn it by yourself. So merge sort and quick sort, both of these are divide and conquer algorithms. They also work in a similar fashion where they keep on dividing the array into smaller and smaller divisions and keep on sorting them, and then finally they again keep on attaching or appending the array and again sorting them and so on. So you can look at the detailed algorithm of merge sort or quick sort. So they are also divide and conquer algorithm. And another we have greedy algorithm. What does it mean that it's a greedy algorithm? So greedy algorithm basically means that it will take the best or the best step at all times. So basically it wants to take the most optimal step at every in every step it will do the most optimal thing. Okay, it wants the best for every single step. It wants the best thing. Okay, so that is why it's called greedy, because it wants the best every time. It wants the best. So an example of this is selection sort. Selection sort is a greedy algorithm because in every step it wants the minimum to be found out, right? In selection sort, we in every pass of the array we find out the minimum element of the remaining array. So that is why, like, that is the essence of a greedy algorithm. Like, it finds out the best one, that is here, say in the selection sort it's the minimum one. It will find out the minimum one and then it will swap it with our current value. So every pass it will find out the minimum one. So that is what it means to be a greedy algorithm. So it takes the best step at all times. Right, this classification is clear. And dynamic programming is something that involves like runtime variables, variable creation and so on, or runtime memory allocations and so on. It is a completely different paradigm compared to these algorithms. We'll learn that, I think, in the last week of the course, week 12. There will be dynamic programming, but yeah, the other three are types of algorithms. Is it clear? Yeah. Okay. Okay, so let's look at the next question. So let's first solve the theory one. So uh, a sorting technique is called stable if, which is the correct answer basically here. So if it takes over n log n time, if maintains the relative order of occurrence of non-distinct elements, if it uses divide and conquer paradigm, if it takes O of n space. So what is the correct answer here? So stable sorting technique. You can try it out by yourself. The answer here is the relative order of occurrence of non-distinct elements. So let's say, what does that mean? Let me define a array. Okay, so let's say this is our array, and we are passing it through a some sorting technique. Okay. Now, finally, our array should be something like this, right? After the sorting, it should be something like this. But if, say, this 5 is this 5 and this 5 is this 5, then only we can say that it's a stable sorting algorithm. That means the relative order of occurrence of non-distinct elements. So here both of these are 5s, right? So they are non-distinct. So the relative order of the non-distinct elements should be the same. Only then we call it a stable sorting algorithm. So here, as you can see, the if the this first 5 that occurs is still after sorting, it's the first 5 that occurs, and the second 5 is the second 5. So that's what we call it as a stable sorting algorithm. So this is a stable sorting algorithm. Now unstable basically just means the opposite, so that if this 5 gets exchanged, like this 5 comes first and this comes second, so we call it unstable. So what are some examples of stable sorting algorithms? So you can try this out by yourself. uh, so stable sorting algorithm, insertion sort is a stable sorting algorithm, okay, and selection sort is unstable. You can check this out, like once you understand the process you can try it out by yourself. So insertion sort is actually a stable sorting algorithm, while selection sort is an unstable sorting algorithm. You can check it out by yourself, but this is the definition of a stable sorting algorithm. All right, now let's look at this question. So it again is a question on insertion sort. So we have this array 5 4 9 1 3. Now it is saying that the cost associated with each sort is 25 rupees. So here again sort means pass. So one step of the sort, one pass. Okay. Now one pass is 25 rupees. What is the total cost of insertion sort when element 1, so this is actually 1. So element 1 reaches the first position of the array. So we start from this particular array A, and how many steps of sorting will it take us so such that this element 1 reaches the top of the array. Okay, and we are of course doing a ascending, so sorting it in ascending manner. That is how this 1 will reach the top of the array. Okay, so let's do the steps. So we start from here. In insertion sort, what happens? This is our first key, right? 4 is our key. We check it with 5. We find that 4 is smaller, so we sort, and it gets sorted to this, right? Now we check. Now in the second step, this is our key, so this is our first pass, or rather I would say, instead of writing first pass here, I would say this is our first pass. Then for the second pass, 9 is our key. We check it with the previous elements. So this is our second pass. Nothing happens because 9 is greater than all of them. So no sorting. No sorting occurs here. Okay. So here swapping happens. Right. Here no swap happens. And we still are at this. Now our key is now 1. Now we check it with 9, we switch. Again we check it with 5, we switch. Again we check it with 4 and we switch. So what happens in the third pass? The third pass you get 1 going to the top, then you have 4, 5, 9 and 3. So this occurs again, like I said, in one pass it will occur. All of it will occur in a single pass. So there will be swapping, and so this is one sort. Okay, so swapping does occur. Swapping occurs here, and then finally 3 will be our key, and we just need one more step of sorting. So 3 and 9 will be switched, will be swapped, then 3 and 5 will be swapped, 3 and 4 will be swapped, and we will finally get our sorted array. That will be after the fourth pass. Okay, but the question asks, when will 1 reach the first portion of the array? So we needed 3 passes to reach, for 1 to reach the top of the array, but out of that, in one pass there was no swapping that occurred, so no sorting that happened. Okay, so for each sort it is 25 rupees, right? So what should be the answer here? Okay, so quite different answers. All right, so the answer here will be, okay, so this is one pass, but okay, even if no swap happens here, this is still, what did we do here? So what happened in this particular step from the in the second pass. In the second pass, what happened? So we checked 9 with 5 and we found that 9 is greater than 5, so we don't need to swap, but it will still be considered as one step of sorting. So this is one step, this is one step, this is one step. So it will be 3 steps of sorting multiplied by 25, answer will be 75. Is that clear to you, or you have anything to say? So the 100, yeah. Uh, okay, so fourth pass is not being considered because here the question asks, what is the total cost of insertion sort when element 1 reaches the first position? So my element 1 reaches the first position after the third pass itself. So technically the question just asks that when element 1 reaches first position, what is the cost associated till then? So I only need to consider the first 3 pass. The fourth pass is only for changing the position of 3. It does not change the position of 1. 1 is already at the first position. So that is why we just consider 3 passes here. The fourth pass we don't consider while calculating the cost, at least from the question. The question asks that. So if they ask only the total cost of insertion sort, I would say 100. 100 is the total cost because we needed 4 sorting steps to get there. But it asks what is the cost of the insertion sort when element 1 reaches the first position. So that only took 3 passes. So that is why I am saying it's 75. Is that, do you agree? Sorry? Okay. All right. Okay. Then we can go to the next question. All right. Now that we have seen the insertion sort just now, let us again do the similar kind of question. So we have um, 10, 4, 7, 23, 67, 12, and 5. Now, it is not told explicitly here, but we are putting it in ascending order. Okay, is that written here anywhere? No, it's not written. So we are putting it in ascending order basically. So what it says, what will be the resultant array A after third pass of the insertion sort? So this we start from here. Let's do the first pass. So in the first pass, what happens? 4 is the key. It gets swapped with 10 because 4 is smaller. So we have 4, then 10, 7, 23, 67, 12, and 5. Right? Now we do the second pass. So 7 is our key. We check, we swap. In the second pass, after doing the second pass, we have 4, 7, 10, 23, 67, 12, and 5. And the next one, we have 23 as the value. So 23, the key. So in the third pass, it's actually, we check it against 10. We find that it is greater than 10, so we don't need to check anything anymore. We just simply go to the next pass. So 23, 67, 12, and 5. So next will be 67. Now we check 67 against 23. We find out that no need of swapping. So from here we will go to the fourth pass. So what is the fourth pass? After the fourth pass, it will become 4 still the same. 23, 67, 12, 5. Now 12 will be the key. Okay. Now you check it against 67. You swap. Check it against 23 and you swap. So this will be the fifth pass. So it will become 4, 7, 10, 12, 23, 67, 5. Now 5 will be our key. We check it against 67. We swap. 23, swap. 12, swap. 10, swap. 5, swap. Okay. So in our sixth pass, we'll do a lot of swapping. And finally, we'll get 4, 5, 7, 10, 12, 23, 67. So this is our entire the insertion sort. Now let's see which of this is matching. So after the third pass of the insertion sort, what is our value? So we have 4, 7, 10, 23, 67, 12 and 5. So option B is correct. Option B is the correct answer. Is this clear? Okay. All right. Now the next question asks which of the inputs will give the worst time complexity for selection sort to sort an array in ascending order. So you have an array, like you are giving it three different inputs. So which of these inputs will take the most number of operations for sorting it into ascending order? Array 2. Okay. Yes, I would say array 2 would take the highest time number of operations. True. But what about array 1? How many operations will array 1 take? And here, okay, so there is a difference between, okay, so when it is asking this is actually different than most number of operations. This is not most number of operations. It is the worst time complexity. Time complexity is always referred in this big O notation of some n square or whatever. So for selection sort, the time complexity, worst case time complexity is n square. Okay, it is not the most number of operations. So if you were asked the most number of operations, I would say the answer is option 2. Option 2, the input number 2 has the most number of operations will be required there. Yes, because it's completely in the descending order. So it is the worst case complexity. But in selection sort, even the best case complexity is also O of n square. So for selection sort, the best case time complexity, best case, what would be the best case? The best case is the array is already sorted in an ascending order. That's the best case. That is input 1. So best case time complexity is still O of n square. So time complexity in this, for all this 3, and average time complexity is also O of n square. So here all 3 of this will give you the same time complexity. So this is kind of a trick question actually. There is no, when it comes to selection sort, there is no best, no worst time complexity. Whatever input you give, it will take the order of n square. Now, yes, if you ask the most number of operations, if we are going and calculating the each operation count, then yes, you can say that operation the input 2 will have the most number of operations to be performed. But if you talk about, yes, yeah, anyway, I'll cover two questions later on, like today, where I will explain the selection sort and the insertion sort again. um, okay, so um, right, so worst time complexity here is O of n square, and the selection sort has a best case time complexity of O n square as well. So the average time complexity is also O of n square. That means it requires at least the order of n square operations. So here there are 8 elements, so it will require order of 8 square operations to be done. Now if the most number of operations are asked, then you can clearly say that option 2 is going to take the most number of operations, because it's the worst case imaginable. But for selection sort, all 3 of this will take the time complexity in the same order, which is n square. So here answer will be both 1, 2 and 3. So is that kind of clear why answer is all 3? Okay. Okay, right now I'll discuss the selection sort. Uh, so what is the best case and worst case time complexity of selection sort? We already saw this just now, and it was O of n square and O of n square. But I will take an example, small one, and I will explain to you how we are calculating that. Okay. So let's say I take this array 54913. I will so best case would be 1 3 4 5 9, right? This is the best case. So I want to sort in ascending. Okay, I'm taking this assumptions. I want to sort in ascending order, and so this is the best case. And the worst case would be if I am given, and this is the input. Okay, this is the input. Now, if the worst case input would be just everything is in descending order, so that would be the worst case input. Okay, so 95431. So this is completely in descending order, and I need to put it in ascending order. So it's the worst case time complexity. So let's count the number of operations. Okay, what happens in selection sort? So okay, in selection sort, what we do is we take the first element. Let's do the worst case first. Okay, so we take the first element. Okay, let's write it down again. No, it's not 2, it's 1. Right, so we'll take the first element and we will compare with the rest of the elements to find the minimum. Okay, in the first pass, we'll assume that 9 is the minimum one. Okay, we'll assume 9 is the minimum one, and we compare it to others, compare it to 5, compare it to 4, compare it to 3, compare it to 1, and we find out which is the minimum element in the array. And we found out that 1 is the minimum element. Okay, this is the minimum element, right? You can see that in currently in this array 9 is the 1 is the minimum element. Now we will swap 9 and 1. Okay, we find out the minimum element, we swap it with our current element. Okay, so after this it becomes 1 5 4 3 9. So we have swapped 1 and 9. So next we take our second element, we do the same process, we compare it to 4, compare it to 3, compare it to 9, we check which is the minimum element. So we found out that 3 is the minimum element. Now this 3 we will switch with 5. This is the second pass. Next okay, so what did we do in this first one? How many comparisons did we have to do? We had to do 4 comparisons, so 4 conditionals, and we had to do 1 swap, right? 4 conditionals and 1 swap. Now in the second one, how many conditional checkings? We compared 5 to 4 to 3 to 9 to find out the minimum one. So 3 conditionals, 3 conditional checking, and 1 swap. So now the array has become 1 3 4 5 9. But still, even if it looks sorted, the algorithm won't stop here. The algorithm will still consider this to be the next case, and it will try to find the minimum. It finds that it's the same, so this is the third pass. It will do nothing, but it has to do 2 comparisons. It will compare 4 with 5, 4 with 9 to find the minimum one. But it does not know that it's the minimum. Like, we can see it and we can say right away, but the algorithm has to run. The algorithm will check 4 against 5, 4 against 9, and it will find, then it will say that okay, no, 4 is the minimum one so far. So you can see in selection sort it checks only with the elements after it. So the part before our key element is all sorted. So here 4 is the key element, and the part before it always is sorted. It will only check 4 against the elements after it. So you are doing 2 conditional checks. Okay, next it will still remain the same, but the next element 5 will be taken as the key in the 4th pass. It will check against 9, right? So you'll do 1 conditional check, no swaps, right? Because 5 is smaller than 9, so there is no need of any swap, and we are done. So how many operations did we require? So if I count the number of conditionals, so it will be 1 plus 2 plus 3 plus 4, right? Plus we have 2 swaps. Okay, Now if I do it for a, so this is for array of size 5, right? This we consider 5 elements in the array. Now if we do it for a array of n elements, so if we have array of n elements, what will this be? So number of operations will be 1 up to n minus 1, because it went up till 4 here, right? We had array of element number of elements 5, so it went to n minus 1, and then we'll have a few swapping operations which might be lesser than n, but it doesn't matter. So 1 up to n minus 1, if you calculate that, it's n into n minus 1 by 2 plus some swappings. Okay, so just the conditional checks. So the swappings will be of a lower order because you have, as you can see, only 2 swappings here. So I'm just considering the conditionals here, which is the higher order term, and you can see that it is n square term is coming, so it is order of n square. Okay, so this is the order of n square. Now what about the best case? So I'll just put this in the bracket like this. This might not be that much better, but yeah, this order of n square. Now what about the best case? Let's see what happens to the best case. 3, 4, 5, 9. Okay, for this case as well, we will take our first element. In the first pass, we will consider the first element. We will check against all the other elements. We'll check 1 against 3, 4, 5, 9, so that we are assured that 1 is the minimum, like the first element is the minimum. So we do 4 conditional checkings here, right? Then our next element is 3. Here we do 3, this is the second pass. We still have to do 3 conditional checks, 3 against 4, 3 against 5, and 3 against 9, in order to confirm that 3 is the minimum one. Then in the next step, we take 4 as the key. We do 2 conditional checks. So in the third pass, we do 2 conditional checks, 4 against 5, 4 against 9, and then make sure that 4 is the minimum one. Then we take the key element as 5 in the fourth pass. We compare it against 9, find out that 5 is still the minimum. So 1 conditional check. So number of operations here. What are the number of operations? 1 plus 2 plus 3 plus up to n minus 1 again. Okay, so n minus 1, if it is up till n minus 1, so this is again n into n minus 1 by 2, which is order of n square. So the best case time complexity is n square, the worst case time complexity also n square. Is that clear how to calculate the best case and the worst case time complexity? So if the best case and the worst case time complexity are order of n square, the average time complexity will also be order of n square. Alright, so now we look at insertion sort. So okay, so what happens in insertion sort? We have already tried out a few examples from insertion sort, so it should be a bit easy. So again, let me write down the same case for both, and we'll see how it is different. So the best case would be 1, 3, 4, 5, 9. The worst case would be 9, 5, 4, 3, 1. Okay, now this is our input. Alright, now let us do the passes for each of them. I'll start with the worst case time complexity. Okay, right, so first 5 will be the key. In the first pass, 5 will be the key. We will check it against 9 and we will swap. Okay, after swapping, what does it become? It will be 5, 9, 4, 3, 1. Cool. Then we take 4 as the key, that is the next element. We start from the second element. Our first pass will take the second element as the key. We start with the second element as key, compare it to the elements above it. Okay, now we check 4 against 9, it is lesser, so it will swap, and then again we check 4 against 5, so again it will swap. So effectively the 4 will go here, the 5 will come here, and 9 will come here. So this is our second pass. Alright, so what happens here? So how many conditional checks are we doing? So we are doing only one conditional check here and one swap. Okay, now here we are doing two conditional checks. So we compared 4 against 9, we swapped it, and then again we compared 4 against 5 and swapped it. So two conditional checks, two swaps. Okay, what happens next? So now we have the matrix 4 5 9 3 1. This is our next key, right? And we check it against 9. We find that it is smaller than 9, so we swap. Then again we check it against 5. We find out that it's smaller than 5, we swap. Again we check it with 4, compare, find to be lower, swap. So basically this goes here and this all comes one step down. So this is in our third pass. So how many conditional checking? 3 conditional checking, 3 swaps, right? Next step. So currently we have 3 4 5 9 and 1. So this is our key. Now we go and we check with 9, swap, then with 1 and 5, swap, then 1 and 4 we swap, 1 and 3 we swap. So effectively this goes at the top. 3 4 5 9 all will come one step down. So in the fourth pass you will have 4 conditional checking and 4 swaps occurring. So number of operations will be 1 up to 4 plus 1 up to 4. So this is the conditional part, this is the swapping part. So if I write in terms of n, so it will be 1 up to n minus 1 plus 1 up to n minus 1. And how much is this? It is twice of n into n minus 1 by 2, or rather it's n into n minus 1, that is order of n square, right? So the worst case time complexity of the insertion sort is O of n square. Okay, now what about the best case? Let's look at the best case. So the best case 1 3 4 5 9. So in the first pass we will have 3 as the key. Okay, this is our first pass and we will have 3 as the key. We'll compare it with 1. We find that it's 3 is greater, so we just stop there. So we did one conditional checking. Okay, the next step what we do is we take 4 as the key and we compare it to the one before it. So we compare 3 and 4. We find that 4 is greater than the previous element, so we stop there. We don't do any more conditional checking because if you remember correctly, the part above the array is already sorted in insertion sort. Okay, so we check with just the previous element. If it is greater than the previous element, then we assume that it will be greater than all the elements before it because they are already in a sorted form. So we check it with 3. We find that 4 is greater. We stop. So in the second pass, we again do one conditional check. Next, what do we do in the third pass? So 5, we check it with 4. Okay, check it with 4. We find that it's greater than 4. So in the third pass, we again do one conditional check. Then in the fourth pass, we take 9 as the key, check it against 5. And we find that 9 is greater than 5, so we just do one conditional check and nothing else. So number of operations Number of operations is, there are 4 operations for this case for size of 5, right? So for size of n, so for array of size n, the number of operations will be n minus 1, right? Now that means the best case for insertion sort is order of n. So the correct answer is option A. Is this clear? How the best case and the worst case time complexity of insertion sort has been calculated? Okay, so that is all I have for you today regarding the sorting algorithms and the searching algorithms. You can refer this PDF and try to do it on your own. Try to take like a simple array like this and try to do the sorting by yourself in order to understand how you're doing. You can also, I'll probably upload this lecture by tonight, so you can watch this again and you can try and follow it, pause whenever you want, and do it on your own in order to understand. If you do it with a few sample arrays, you will be able to get it eventually, how the sorting is taking place. So, and then I have told you how to calculate the best case and the worst case time complexity. So in this case, the best case is O of n, worst case is O of n square. So average time complexity, what is the average time complexity? So if you average it out, O of n and O of n square, your average will come as O of n square, right? Because that is the bigger term. So that will be the one which will be the leading term in the calculation. Okay. So unless there are any further questions, we will stop here. So I have put the link. So I put the link to the previous lectures and the PDFs in the chat already. You can make use of that. I will upload this PDF as soon as the class is over. I will upload this PDF, and later at night, you can see the video as well. I will also put the link to the video, so you can you can see the video and the PDF. So that should help out, I feel. Okay, if there are no further questions, then I will close the meeting here. Thank you for joining, and we'll meet again in the next week, Tuesday, 6 to 8 p.m. for discussing the week 10 questions. Thank you.